Second life, just pwn this program using a double free and get a flag. It's found in this location on the shell server. Now the hint from Afterlife gave me a set of flags from the University of Indiana. This is going to look at dlmalloc, so Doug Lee's memory allocator. And this is described as the program mentions in the book Secure Coding in C by Robert Secord. So this is one of the examples from that book. Okay, so what we see here is we do a malloc. We then get to see the address of that malloc. And then there's going to be some more mallocs. The key thing that happens here is we have first gets freed twice. And when first gets freed twice, what will end up happening is that 6th and 7th will both get that same address that first had. And in fact, every malloc after that for a 256 byte chunk will get that same address. As we look at Doug Lee's memory allocator, we see that allocated chunks and deallocated chunks, in order to minimize memory, some of the header information for an unallocated chunk, namely the pointers to the previous and the next unallocated chunk, occupy the same space as user data for when a chunk is allocated. And that's going to be really important. So these chunks are stored in a doubly linked list of free chunks. When they're free, this previous in use bit is set here or not. And then this is the size of the chunk. When we free something, it gets unlinked from that doubly linked list. And so here what we're going to do is there's this macro. So we want to go to the forward one and change its back pointer. And we want to go to the previous one and change its forward pointer. So these black arrows become these red arrows. But what we get to do here is we are going to actually have untrusted user data here. Because remember what I told you is that 6th and 7th are the same chunks. So when it tries to allocate 7th, it thinks it needs to unlink it, but it's already been filled with data from when we read to 6th. So I'll show you that again. So we allocate 6th, we get to write data to it. Then when we malloc 7th, it thinks it needs to unlink 6th because 7th and 6th are the same from the free list. So we get to modify these pointers. We're going to do 2 writes, and they're shown right here. So this back pointer, so forward, this one, back is plus 12. So 12 offset from this pointer gets set to this one, and 8 offset from this pointer gets set to this one. So as we look at our code for the exploit, we'll see here that I'm saying I want exit, the got entry for exit. So exit is going to have a pointer in memory to its location. We're going to change that to be the address of our shellcode. And so we're going to take exit minus 12 because this forward arrow back is going to add 12 to whatever FD is. So we add 12 to that, we get the address of got. We're going to change that to be first plus 8 because first is going to contain this data followed by this data. So 8 bytes in will be the beginning of our shellcode. So we're making exit point to the beginning of our shellcode. Now it's also the case that back arrow forward, so 8 more bytes after first plus 8, so 8 bytes into our shellcode is going to point back at exit minus 12, which means that our shellcode either needs to be shorter than 8 bytes, which it is, or we would need to then jump over the 4 bytes that get trashed by the link going in the other direction. So this right here is what's in the forward pointer. And so forward arrow back, so 12 bytes into that, we replace with the other address. So exit minus 12, or plus 12, so the address of exit in the got gets replaced with the address of first plus 8. First plus 8 plus 8, so first plus 16 gets replaced with the address of exit in the got minus 12. And again, that's going to be past the end of our shellcode, so we're not going to care. So we're going to send that as the data for 6th. So when 7th does the unlink, exit gets to point to first plus 8, which is going to be this shellcode, which pushes the address of win onto the stack and then returns there. All right, so sort of walking through the slides here, we have an empty bin, we allocate a chunk. The first call to free, it's the only thing in that doubly linked list. And we call free on it again. What ends up happening, because it doesn't really expect free to be called on something already in the free list, is we get this data structure here. So once we get this data structure here, every time we call malloc, it's going to return this block. And when it unlinks it, this block will still be there. So we'll just return this block over and over again for every malloc after the double free. So in our code, we've freed first twice. So after that point, 6th and 7th both get the address of first passed to them. And as I said, because of the unlink, we're making the address of exit point to first plus 8, which is this shellcode. So when we run this, we've overwritten the address of exit in the GOT with the address of this shellcode, which just pushes the address of win and returns there. And so therefore we get our flag, heap flag. And there we go.